Alright, here we go. Number 1. Describe a use for the remainder theorem. So you can use the remainder theorem to evaluate a polynomial, f of x. Let's say, I'll just write an example. F of x equals 3x cubed minus 2x squared plus x minus 1. Alright. So what's f of 10? Well, you can directly substitute 10 for x, which is the way we're used to doing it, but you can use a remainder theorem, and it goes a little bit faster if you use a remainder theorem to evaluate. What we get is, let's use synthetic division on this. Make that a positive 10, not a minus. We're evaluating f of 10, so here we go. And we'll write the coefficients. We've got a 3, negative 2, 1, negative 1. Alright, bring down the 3. 10 times 3 is 30. 30 minus 2, 28. 10 times 28 is 280. 280 plus 1 is 281. And 10 times 281 is 2810. 2810 minus 1 is 2809. And this is the remainder when you divide this polynomial by x minus 10. And that happens to equal f of 10. Alright, right here, the remainder is f of 10. Alright, so in my opinion, it's easier to use synthetic division and the remainder theorem to evaluate f of 10 than it is by using direct substitution. Alright, of course that may not always be the case. Sometimes it may be easier to use direct substitution. But in many cases it's easier to use the remainder theorem. So, as I've always been advocating, it's always good to know more than one way to do things in mathematics. Okay, sometimes these alternative ways can come in handy. So, in general, the remainder theorem says that if a polynomial is divided by x minus k, then f of k equals the remainder. All right? If the polynomial is divided by x minus 10, then f of 10 equals the remainder. That's putting in our specific particular case here into the remainder theorem statement. All right? So, there it is. Number 3. What is the difference between rational and real zeros? Well, rational zeros are just rational numbers, which are zeros of a polynomial, and they're real numbers. All right, they are real numbers. Rational numbers are a part of the real numbers, the set of real numbers, but there are some real numbers which are not rational. For example, pi is not rational. Square root of 2. There are proofs for square root of 2, by the way, famous old proofs, being irrational. You can write a rational zero as a fraction. That's basically what a rational number is. It's a number that can be written as a fraction. So that would include integers. Integers are like 1, 2, 3, 4, 5, 0, negative 1, negative 2, those sort of things. You can write, for example, 5 as 5 over 1. That's written as a fraction. All right. So integers are a part of the rational numbers, but there are rational numbers which are not integers, like 1/2. All right. So written as decimals, rational zeros can either terminate or repeat, like oh, 1/2 is 0.5. That terminates. All right, then you've got numbers like 0.11111, and it keeps repeating. All right, those are also rational. But irrational numbers written as a decimal neither terminate nor repeat. Okay, like pi, for example, 3.14159. But it keeps going. It keeps going after that 9. All right. If you remember just 3.14 equals pi, well, that's an approximation. Okay, that's not the exact representation for pi, in decimal form. Okay, so or you may remember a shortcut like pi equals 22/7. All right, that's also an approximation. Pi cannot be written as a fraction. It's not a rational number. All right, so you can't write it as 22/7 except as an approximation. So if you're thinking pi equals 22/7, well, that would be incorrect. Okay, it's approximately equal to that. It's approximately equal to 3.14, all right, but it's not exactly that number, okay? Okay, 5. If synthetic division reveals a 0, why should we try that value again as a possible solution? Pardon me, I'm eating a peppermint candy Altoid. Because you can have repeated zeros, okay? In other words, you could have roots of multiplicity greater than 1, okay? So if you do synthetic division and you get a remainder of 0, you found a root. A root is another name for a 0. It's the older name for 0, which I'm used to, by the way. I'm used to root. 0 is 2 syllables, root is 1 syllable, so it's easier to say anyway. All right, so, but let me give you an example here, a specific example, which isn't in your book. F of x equals x cubed minus 9x squared plus 27x minus 27. I want to find the zeros, okay? Now it turns out that 3 will work as a 0, so let's try a 3. Alright. So we get a 0 remainder, and let's say we want to find another root. Try 3 again. That's a standard procedure, all right? In case you have a root of multiplicity greater than 1, try it again. And you could do it on the line just below here instead of rewriting the whole thing again. This is a nice way of making that easier. Just draw another line like that. The remainder goes under the 9 here, and you just ignore that 0 remainder there. All right, so lo and behold, we get another 0 remainder. I wonder if 3 will work again. So at this point, you know, you don't need the synthetic division. This represents x minus 3. Okay. You can set x minus 3 equal to 0 and solve for x. X equals 3. Well, let's try synthetic division anyway. Just for kicks. And negative 3 plus 3 is 0, so there you go. Alright. So that's as far as we go on this. And f of x, well, the root is 3 multiplicity 3. 3m3. Alright. So that means f of x can be written like this in factored form. X minus 3 quantity or rather x minus 3 to the third power. Alright? And if you multiply that out, you will find that when you multiply all this, cube it, you'll get that back again. Alright? Number 7. For the following exercises, use the remainder theorem to find the remainder. So what we have here is 3x cubed minus 2x squared plus x minus 4 divided by x plus 3. By the way, the reason we're using parentheses should be clear to you by now, but just in case, if these parentheses were left off, let me just focus in on this area right here of this line here. You would have something that looks like this, minus 4 divided by x plus 3, and then let's see, you have a x here, over here. That's what you would have, and so this would represent x minus 4 over x plus 3. Alright? That's, in fact, what that equals. Alright? It equals this. It doesn't equal, you're dividing all of this by all of that. Alright? So you must use the parentheses. Unless you write it vertically, write this as a fraction, this over that. You could do it that way as well. But if you're writing it horizontally, you have to have those parentheses, otherwise you're going to get this. Okay? So even if that looks okay to you and you end up with the right answer, if I were the teacher, I would mark you off at least some points for writing it that way, because that's really incorrect. And this kind of stuff leads to a lot of errors in math, and you can find those a lot on Facebook. People will write these math problems and say, what's the answer? And you have to understand order of operations and so forth to get the right answer, and a lot of people just totally mess it up. But anyway, I'm going a little bit off on a tangent here, so this isn't geometry, so let's get back on topic. Alright, so now this is x plus 3. Alright, the remainder theorem, or synthetic division, assumes that's x minus k. So this is going to be x minus a negative 3 to make that equal to x plus 3. So you write a negative 3 there. Okay? If that said x minus 3, you would just write a 3. When it says x plus 3, you write a negative 3 there. Alright? So look out for that little detail, because that can lead to a wrong answer. One little wrong sign and you gotta go back and correct. Alright. One thing math teaches you is attention to detail, unlike anything else, I think, or a lot of other things. And attention to detail is good. If you're building a bridge or an airplane or something, or a critical electronic components, yeah, I'm glad they pay attention to details, don't you? If you're riding in an airplane and somebody forgot something, maybe you might crash and burn, alright? So, anyway, the remainder is right there in this its own little box, negative 106, alright? Okay, number 9. I'm starting to get smart, and I think I'll write it out beforehand here to save some time. So we've got x minus 4. So you put a 4 there. You got your coefficients. Bring down the minus 3. Let's see, 4 times that is negative 12. Add the 6, you got negative 6. negative 24, and add those, you get a 0 remainder. Alright, so the remainder is 0. Number 11. So it's already up there, and write our 4, and you've got a 1x to the 4th. Now there are no x cubes, x squareds, or x's, so you have to put their placeholders there, 0x cubed, 0x squared, 0x, and then finally the minus 1, the constant term. If you don't put these zeros in, if you're missing quote-unquote missing terms, then you're going to get the wrong answer. Okay, so look out for those. 4 times 1 is 4, 4 plus 0 is 4. 4 times 4 is 16. 16 and 0 are 16. 4 times 16 is 64. 64 plus 0 is 64. 4 times 64 is 256. 256 minus 1, 255. So the remainder, 255. Number 13. So we're dividing by x plus 2, that's x minus a negative 2, so you write negative 2 in the corner. You got 4, 5, negative 2, 7. Okay. So our remainder, negative 1. Number 15. For the following exercises, use the factor theorem to find all real zeros for the given polynomial function and one factor. So they're going to give us the polynomial and a factor. And then we have to find all the real zeros. So f of x, here's our polynomial, 2x cubed plus x squared minus 5x plus 2. And the factor they've given us is x plus 2. So that's the same as x minus a negative 2. So since this is a factor, we can divide like this. Use that minus 2. You're going to divide this polynomial by that, and then you're going to see what you get. Okay, and we're expecting a remainder of 0 since this is supposed to be a factor. If we don't, then either the book's wrong or you made a mistake, or I made a mistake, okay? But it does work. So if your math is correct, you should get a 0 remainder out of this. So we've got, let's see, negative 4 up here, that's negative 3, positive 6, 1, negative 2. So there's our 0 remainder that we expected. Okay, so this line right here means that f of x is equal to x plus 2 times 2x squared minus 3x plus 1. Alright. It was originally x cubed, so this is 1 degree less, 2x squared minus 3x plus 1. Alright, so you can write f of x in a factored form once you get to this line, like that. Okay. Now, it turns out that that's not a repeated root, negative 2 doesn't work again. So to save time, I'm going to tell you what to use here. Use 1. All right. Later we'll be using rational zeros theorem, and we'll be able to get a more of a clue as to what to use here. But for now, just use the 1. Trust me on this. Okay, I told you, that works. See, there you got a zero remainder. So this line right here means that f of x, what I've done is basically I've factored this quadratic. So f of x is now equal to x plus 2 times, you've got your x minus, that means x minus 1. And here, that stands for 2x minus 1. Okay. So, now you can do synthetic division again if you wish, but it's very easy just to write 2x minus 1 equals 0. It's like if you take this polynomial and solve it for all of its zeros, you set each factor equal to 0 and solve separately, right? So what I'm doing is I'm setting that equal to 0 and solving that for x. So x is equal to a half. So our zeros, or our roots, are minus 2, 1, and 1/2. Okay, number 17. So here's our polynomial, here's our factor. Alright, so this is x minus a negative 2. So write negative 2 in the corner. And you've got 2, 3, 1, and 6 for the coefficients of the polynomial. Alright, on with the synthetic division. And we were expecting a zero remainder. So this line represents f of x equal to x plus 2 times 2x squared minus x plus 3. X squared minus x plus 3. It's an x squared because it's 1 degree. A degree is 1 less than what we started with, okay, from the division process. Okay, so what are we going to do with this? Well, not much. All right, we need to find the direction said find the real roots. This does not have real roots. All right, this right here, this quadratic does not have real roots. How do you know for sure? Well, you can try various numbers up here and none of them will work, but there are easier ways. You could try using the quadratic formula or completing the square on this. Okay, there's an even easier way. You use the discriminant. That comes from the quadratic formula. Discriminant it discriminates between your rational and irrational and non-real roots. That's why they call it a discriminant. The discriminant is b squared minus 4ac in a quadratic function or polynomial. Alright, so in this case b squared minus 4ac is equal to, so a is 2, b is negative 1, c is 3. Alright, so you've got, let's see, negative, what is it, negative 1 squared minus 4 times 2 times 3. Okay, so that equals 1 minus 24, which equals negative 23. That's less than 0. If it's less than 0, the discriminant, that is, there are no real solutions, all right? If it equals 0, there's only one rational solution. And if it's greater than 0, then you've got two irrational solutions. Okay, so look that up in your book, discriminant. It comes from the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Remember that? That's the quadratic formula. This under the radical here is the discriminant. All right, which we just figured out. So this under the square root sign is less than 0. It's square root of negative 23. So you're going to have negative b plus or minus the square root of negative 23 over 2a, all right, as your solutions. Now this is going to involve I, the imaginary number I. All right, you've got two non-real solutions. Okay, if this were to equal 0, you'd have the square root of 0, which is 0. So all you'd have is negative b plus or minus 0, which you can just forget about the 0 part. It's just minus b over 2a. That's just one solution, and it's a rational number, minus b over 2a. Okay. Now, if this is greater than 0, well, you have two real solutions, actually. I said irrational. That was not quite right. Okay, it could be irrational. If you have like the square root of 2 or something, that would be an irrational number. But if it was square root of 4, you could take that square root and you would end up with two rational solutions. All right, so you could either have irrational or rational number solutions if this is greater than 0. Okay, so that's how that discriminant works. But anyway, there's only one real 0, which would be minus 2. Minus 2. So minus 2 is the only real number 0 here. Okay. $19. All right, so x minus a negative 3. So we got a negative 3 and a 1, 3, 4, and a 12. Okay, this right here, we started with an x cubed, so that's an x squared plus 0x plus 4, or x squared plus 4. Okay, so this polynomial can be written as x plus 3 times x squared plus 4. All right. X squared plus 4 doesn't have any real solutions, though. You can try the discriminant on that one. A is 1, B is 0, C is 4. Or you can just write x squared plus 4 equals 0. It's pretty easy. So x squared equals negative 4. All right. And x equals plus or minus 2i. Okay, so these are not real solutions. All right. So you only have one real solution. That would be negative 3. Or one real 0. One real root. Negative 3. Okay, 21. All right, now before we can use synthetic division on this, we have to write that as x minus k. All right, this is the leading coefficient has to equal 1 in order to use synthetic division. Okay, we've gone over this before in a previous section. All right, so I went ahead and did this. If you're wondering how I did this, go back to the previous section with synthetic division, And we ran into a few problems like this, and I covered those in detail. All right. So we're dividing this polynomial now by x minus a negative 5/2. So I write negative 5/2 up here. And the coefficients of this polynomial, not this one. All right. So you got 1, 5/2, negative 6. Oops. Need some space there. And negative 15. So, oh, what a relief they add to 0. Haha. We don't have to add fractions. Oh boy. Well, don't worry, we're going to get somewhere we do have to add fractions. Okay, so you might want to review adding fractions. And let's see, we've got 15. All right. Now we can use synthetic division again on this. That represents x squared minus 6. But it's a lot easier just to write x squared minus 6 equals 0 and solve. So x squared equals 6, and then take the square root of both sides. And remember, there's a positive and a negative square root, so you write plus or minus square root of 6. That's an irrational number. Okay, so we have negative 5/2 as one root, or 1, 0. And we have plus or minus the square root of 6. So there are 3 real roots, or 3 real zeros.